Hello everyone and welcome back. Well, in the previous lecture we have dealt with the very first lemma of graph theory, that is the handshaking lemma, more popularly known as the degree sum formula. We have learnt that in any graph the total sum of the degrees of all the vertices taken together is twice the size of the graph, that is 2 times the number of edges present in the graph. In that sense, we have learned that the degree sum of any graph is an even quantity. In relation to that, we have also discussed that the total number of odd vertices in any graph can never be odd. We will always have an even number of odd vertices in any graph. Apart from these, we have also discussed some other few lemmas and corollaries as an application of the degree sum formula. And towards the end of the previous lesson, I have posted one numerical problem based on handshaking lemma for your practice, which I am definitely going to solve now in the very beginning before I move into the topics of discussion for today's lecture. Now, before I solve the problem, let us look into the question once again. Now, the problem was, we are given a graph having order 5 and size 9. There is one vertex of degree 5, one vertex of degree 1, and the remaining vertices have the same degree x. So, our job was to determine the value of the variable x. So, let us list down the given information from the question. So, we have been given a graph whose order is 5 and whose size is 9. There is one vertex of degree 5 and one vertex of degree 1, and the remaining vertices, now let us count here only how many remaining vertices we have. So, remaining vertices, that is total number of vertices was 5, out of which there was one vertex of degree 5 and there was one vertex of degree 1. So, remaining we have 5 minus 2, that is 3 vertices. So, remaining 3 vertices have degree x each. Now, our job is to find the value of the variable x. So, we will directly apply the degree sum formula, which indicates that the sum of the degrees of all the vertices in a graph, in any graph, is equal to twice the size of the graph. So, how can we find the sum of degrees of all the vertices here? We have one vertex of degree 5, we have one vertex of degree 1, and we have 3 remaining vertices each of degree x. So, this is the degree sum of this graph, that is equal to twice the size of the graph. Now, the size of the graph is given as 9. So, this is nothing but equal to 18. So, if we simplify this, we get 5 plus 1 plus 3x equal to 18, which implies 3x equal to 18 minus 6, that is 12, which provides us the value of x as 12 by 3, that is 4. Therefore, the solution to this problem is x is equal to 4. So, the remaining 3 vertices have the degree 4 each. So, this is the solution to the problem as presented on this slide. You can look into this for your reference. So, now we start today's lecture, and the topics of discussion today include the degree sequence of any graph. Then we will learn what we mean by graphic sequence or graphical, and finally we will be discussing a very important theorem, that is the Havel-Hakimi Theorem, that will help us to identify whether any given sequence is a graphic sequence or not. So, let us start today's lecture with the very first topic of discussion, that is degree sequence of a graph. Now, in previous lecture we have already discussed how we can calculate the degrees of all the vertices present in a graph. Now, having found out the degrees of all the vertices in a graph, when we list these degree values in a sequence such that it maintains a non-increasing order, a non-increasing fashion, then we say that the sequence is a degree sequence of a graph. So, basically what we do, suppose this is my graph G with vertices A, B, C, D and E. Let me write the degree values of the vertices within brackets. So, A has degree 3, B has degree 2, C has degree 4, D has degree 2 and E has degree 1. Now, after we have found out the degree values of all the vertices, if we list down these degree values in a non-increasing sequence, that is starting with the largest degree value, that is 4, followed by the second largest 3, then we have 2 vertices having the degree 2 each. So, we will list down both the degree values 2 and again followed by 2 only. Finally, we have a degree value, that is 1 for the vertex E. So, if we list down the degree values of a graph in a non-increasing sequence starting with the largest degree value till the smallest one, then that particular sequence will be called a degree sequence of the graph. So, this is the degree sequence of this graph G. And in general, the degree sequence of any graph is either denoted by D or it is sometimes denoted by the letter S also. So let's see another example. Suppose we have this pseudo graph and the vertices have degrees 3, 4 and 3. Now if I list down these degree values in non-increasing sequence, then I have the sequence as 4, then 3 and then again a 3. You cannot neglect any multiple appearance of the degree value. You have to put all of them. So this is degree sequence of the graph G. Now see, given a degree sequence, just looking into it, you can say how many vertices the graph has or what is the order of the graph. See, there are 3 terms in this degree sequence which indicates the graph has 3 vertices, out of which one vertex has degree 4 and the remaining 2 vertices have degree 3 each. Okay, so the size of the degree sequence, that is how many terms you have in that sequence, will indicate the order of the graph. So let's see the definition. If the degrees of the vertices of a graph G are listed in a non-increasing sequence S, or sometimes we denote it by D, then that sequence is called degree sequence of that graph G. We can see for another example. Okay, so I have drawn a K5 here. There is a complete graph on order 5 and the degree values, as we know, in K5 it is 4 regular graphs, so every vertex is having degree 4. So here each of these vertices have degree 4. Now if I list down these degree values in a sequence, then I have only 4, 4, 4, 4 and 4. So the sequence consists only of 4 but 5 times. You have to write it 5 times, each time for each vertex. See, clearly it indicates the order of the graph is 5. So this is the degree sequence of K5. Now see, when we are writing the degree sequence, what we are doing basically is we are writing the degree values of all the vertices in a graph. Now what will happen if I add all the terms of a degree sequence? For example, this is a degree sequence D. If I add up all these terms of a degree sequence, I am going to get an even quantity, and that even quantity is nothing but twice the number of edges in the graph, because this follows from the degree sum formula itself, that the sum of the degrees of all the vertices in a graph is twice the size of the graph. So this degree sequence is nothing but a sequence consisting of all the degree values of the vertices in a graph, and all the degree values of the vertices are present here. So if I am summing them up, I am basically calculating the sum of the degrees of all the vertices. That by the degree sum formula has to be even, that is, it is equal to twice the size of the graph. For example, see in this graph, the total sum of the terms of this degree sequence is 4 multiplied by 5, that is 20. And we know in K5 we are having 10 edges. So this sum, that is 20, is nothing but twice the size of the graph. This is the degree sum formula. And the degree sequence is nothing but the degrees of all the vertices present in a sequence. So that leads us to a proposition that a sequence of non-negative integers d1, d2, d3 up to dn will represent the degree sequence of some graph if and only if the sum of all these terms is even. So basically, if you are given a sequence of non-negative integers, non-negative because degree of any vertex can never be negative, it's either 0 or it is a positive integer. So if we are given a sequence of non-negative integers such that the sum of all the terms present in the sequence is an even quantity, then definitely that sequence is a degree sequence of a graph. That means a graph can be drawn with that sequence as its degree sequence. For example, if we have a sequence, I have just written a random sequence of non-negative integers, just keeping in mind that the sum of all these terms is an even quantity. Now it is 14 here. So the moment I see that the sum of all these non-negative integers present in the sequence is an even quantity, I can conclude that D is a degree sequence. That is, a graph is possible to be drawn with this sequence as its degree sequence. For example, I can show you, if this is the degree sequence of a graph, then we are having 5 vertices in that graph as it is indicated by the number of terms present in the sequence. See, I can draw a graph in which there are 5 vertices where the degree values are 4, 4, 3, 2 and 1. So, whenever the sum of the terms present in a sequence of non-negative integers is even, it is definitely possible to draw a graph with that sequence as the degree sequence of the graph. Now, let us see some more examples. Here we are having a graph in which the degree values of the vertices are 1, 1, 4, 2 and 2. So, the degree sequence goes like this, starting with the largest degree value, that is 4, followed by 2, then again a 2, then we have a degree value 1, again a 1. So, this is the degree sequence of this particular graph, where the number of terms in the sequence is clearly indicating the order of the graph. And you see, the sum of all these terms present in the sequence is equal to 10, that is an even quantity. It has to be even because the sum of these terms is nothing but the degree sum of the graph, and the degree sum of any graph is always even because it is twice the size. Here we have a pseudo graph. So the degree values of the vertices when listed down in non-increasing sequence, we get 5, the largest one, then 2 followed by 1 and then 0 for the isolated vertex. See, we are having 4 vertices in the graph, that is indicated by the number of terms in the sequence. The sum of the terms of the sequence is 8 and that is also an even quantity. Now, given a sequence of non-negative integers, if we find the sum of those terms is not even, it's odd, then clearly we can conclude at that moment itself that the sequence is not a degree sequence. That is, a graph is not possible to be drawn with that sequence as its degree sequence. And the moment the sum turns out to be even, we immediately conclude that the sequence is a degree sequence, that is, a graph is possible to be drawn. Let's take another example. Suppose I have this sequence 4, 2, 0. Now here the sum of the terms is 4 plus 2 plus 0, that is 6, which is even. Immediately we can conclude that D is a degree sequence of some graph. And what do we mean by this? We mean that a graph is possible to be drawn with this sequence as its degree sequence. So if we try to draw any such graph, we will be having 3 vertices as it is indicated by the terms itself, out of which there is one vertex of degree 0, so one vertex has to be isolated. There is another vertex of degree 4 and a vertex of degree 2. So I can make a loop at a vertex so that its degree becomes 2. This is the isolated vertex whose degree is 0. And there is a vertex of degree 4, so this is the third vertex having degree 4. So I can make 2 loops at that vertex so that its degree becomes 4. So this is a graph G in which I am having 3 vertices whose degree values are 4, 2 and 0, giving me this degree sequence. Now I could have drawn another graph also by drawing multiple edges. For example, I could have drawn 2 multiple edges here and a loop here, so that the degree value of this vertex would be 2, it is 0 and this is having degree 4. See, this is also a graph different from the first graph but having the same degree sequence. So basically the conclusion is, if the sum of the terms is even, it is possible to draw a graph with the sequence as the degree sequence. Now the question arises, is it possible to draw a simple graph? Now see, both the graphs that I have drawn, I have taken the help of loops or multiple edges. Now can I draw a graph with this degree sequence without taking the help of loops and multiple edges? That is, can I draw a simple graph with this sequence D as its degree sequence? Now the answer is no. It is not possible to draw a simple graph having 4, 2, 0 as its degree sequence. However, if I take a different sequence, say 3, 3, 2, 1, 1. Now see, here the sum of all the terms is 10, which is even. Since it is even, so I am concluding that D is a degree sequence of some graph. That is, graph is possible. I can draw graph with this sequence as degree sequence. Now I could definitely draw a graph with loops and multiple edges if required. For example, I could have drawn it like this. There are 5 vertices in the graph as there are 5 terms in the sequence. 2 vertices have degree 3 each, so I can make loop at 2 vertices and make them adjacent, so that both of them will have the degree 3. There is a vertex having degree 2 and there are 2 other vertices which are leaves. See, this is a graph which satisfies this degree sequence D, 3, 3, 2, 1, 1. Now here I have taken the help of loop. Now can I draw a simple graph with the same degree sequence? Yes. I could have drawn the graph like this. A vertex having degree 3, another vertex having degree 3, this is a vertex having degree 2 and these are the vertices having degree 1 each. So this is another graph that I have drawn with the same degree sequence D but without taking the help of any loop. So this is what I have drawn, a simple graph. But for the earlier example, it was not possible to draw a simple graph with that degree sequence 4, 2, 0. But with this degree sequence, I can draw a simple graph also. Now this gives rise to the concept of graphic sequence or graphical. So how do we define a graphic sequence? A graphic sequence or graphical is basically the degree sequence of a simple graph. That is the definition. So let's summarize this. Given a sequence of non-negative integers, if we find the sum total of all the terms is even, we conclude that the sequence is a degree sequence of some graph. That is, it is possible to draw some graph with that sequence as its degree sequence. May not be simple, may be simple. Now the moment when you know that a simple graph can also be drawn with that sequence as its degree sequence, that is when we call the sequence a graphic sequence or graphical. So a degree sequence will not be termed as graphical unless it is concluded that a simple graph can be drawn with that sequence as its degree sequence. So let's see the definition. A finite sequence of non-negative integers is called a graphic sequence or graphical if it is the degree sequence of some simple graph. This is important. And in case if we have D as a graphic sequence, then we use this particular phrase that the graph G realizes D or D is a realization of G. So if D is a graphic sequence, that is a simple graph, suppose G can be created with this sequence D as its degree sequence, then we say D is a realization of the graph G or the graph G realizes the sequence D. That is a phrase, you can remember it in that way. Let's see some graphic sequences now. So in this graph, see, we are having the degree values as 1, 1, 3, 3, 2. So if we list it down in non-increasing fashion, we have it as 3, 3, 2, 1, 1, which is the degree sequence of this graph. And if you observe carefully, you will find the sum of all the terms present in this sequence is an even quantity. Apart from that, you can see that a simple graph G can be drawn with this sequence as its degree sequence. So this is not only a degree sequence, but this is also a graphic sequence or a graphical, because it is possible to draw a simple graph with this sequence. Now let's solve some problems and check if some particular sequences are graphic or not. Now the first question is for this particular sequence to check whether it is graphic or not. So our first and foremost duty would be, given any sequence, first find out the sum of the terms of the sequence. And if the sum is odd, immediately conclude it is not a degree sequence. And if some sequence is not a degree sequence, then it can never be a graphic sequence, because to be a graphic sequence, first of all it has to be a degree sequence. When it is degree sequence, then we proceed further to check whether it is graphic or not. So first we will find out the sum of all the terms. Here it is 3 plus 3 plus 2 plus 2 plus 1 plus 1 plus 1. So the sum is 13, which is odd. Now the moment you see the sum is not even, immediately you conclude, if this is your sequence D suppose, then D is not a degree sequence. That means not even a graph is possible to be drawn with this sequence as its degree sequence, because the sum total is not even. Now for a graph, by the degree sum formula, we know the sum of all the degrees has to be even. So if it is not even, graph is not possible. And if graph is not possible, definitely simple graph is not possible. So D is not a graphic sequence, or it is not a graphical. So this is the solution written on this slide, where we have mentioned the exact logic why this given sequence is not a graphic sequence. The reason is it violates the degree sum formula, as the sum of all the terms present in the sequence is not an even quantity. Let's check for another problem. So here the sum of all the terms would be 20. Sum is even quantity. Now once you know it is even, therefore we know that the given sequence, if it is D, then D is a degree sequence. The total sum being even can only let us conclude that it is a degree sequence. Now we have to check whether it is graphic sequence or not, because that is the question, whether it is graphic or not. Now see, the sequence present here contains 7 terms. That means the graph that will have this sequence as its degree sequence will have 7 vertices in it. Now if this sequence has to be graphic sequence, then it should be possible to draw a simple graph with this sequence D as its degree sequence. Now that graph will be having 7 vertices in total, no doubt, as there are 7 terms in the sequence. Now see, there is a term 7 in this sequence, which indicates there will be a vertex of degree 7 in the graph. Now recall, in some previous lecture when we have discussed about complete graphs, we have learnt that in any simple graph on n vertices, the maximum degree that a vertex can have is n minus 1, because you don't have the liberty of having loops or multiple edges in a simple graph. So in any simple graph of order n, where there are n vertices, the maximum degree that a vertex can achieve is n minus 1, and that is by being adjacent to all the remaining n minus 1 vertices. Now in a simple graph of order 7, you can never have a vertex having degree 7. The maximum degree that a vertex can have in a simple graph of order 7 is 6, that is 7 minus 1. So having a simple graph with order 7 in which there is a vertex of degree 7 also is not possible, and that is the reason this sequence D is not a graphic sequence. So although this is a degree sequence, that is a graph is possible, but a simple graph is not possible. That is why it is only a degree sequence but not a graphic sequence. So you could have drawn graphs with the help of loops and multiple edges satisfying this sequence as its degree sequence, but it is not possible to draw a simple graph without taking the help of loops and multiple edges with this sequence as its degree sequence. So the given sequence is not graphic. This is the solution to the problem which is presented on this slide. You can go through it. Next we have a sequence with 4 terms. Let us first find out the sum. That is the most important part to do. Before going to check whether a sequence is graphic or not, first check whether it is a degree sequence or not. So first find out the sum. The sum is 10, which is even. So this implies the sequence D is a degree sequence. Graph is possible. Now whether it is graphic sequence, that is whether simple graph is possible or not. Now let's see. There are 4 terms in the sequence, that means the graph is going to have 4 vertices in total. Now if it has to be a simple graph, see there are 3 vertices having degree 3 each. Now in a graph of order 4, if it has to be a simple graph and a vertex has to have the degree 3, then the only possibility is it has to be adjacent to all the remaining 3 vertices. Now like this, there are another 2 vertices having degree 3 each. So suppose this vertex has degree 3, then it has to be adjacent to all the remaining 3 vertices. There is another vertex of degree 3, so we have this as the possibility. Now when there are 4 vertices in the graph, out of which 3 vertices are having degree 3 each, that indicates there is no vertex in the graph with degree 1. The minimum degree in the graph is definitely greater than 1. So it is not possible in a simple graph having 4 vertices in which 3 of them are having degree 3 each, you cannot have a vertex of degree 1. That is not possible. Hence this sequence is not a graphic sequence. So this is the solution to the problem with the logic that since there are 3 vertices having degree 3 each, so if this is the case in a simple graph, then the minimum degree in the graph is definitely greater than 1. There cannot be any vertex having degree 1. That is why this sequence is only degree sequence, but it is not a graphic sequence. So basically we have gone through some particular problems and we have given some logic to decide whether the sequence is a graphic sequence or not. Now given any arbitrary sequence, it is not always possible to get hold of the correct logic to decide whether it is graphic sequence or not. If the total sum comes out as odd, it is easy for us to conclude that it is not a graphic sequence because it will not be a degree sequence even. Otherwise, if the sum comes out as even, then we know it is a degree sequence. Then to identify whether it is graphic or not, it's not always easy to find the proper logic. So in that scenario, we have been provided with a very important theorem called the Havel-Hakimi Theorem, which will help us to identify any given sequence whether it is graphic or not. So let's go through the statement of the Havel-Hakimi Theorem. As we can understand, it's very important one as it will help us to identify whether a given sequence is a graphic sequence or not. So let's see the statement of the theorem first. Then we will solve some examples and it will be more clear. So the theorem goes like this. For n greater than 1, an integer least d of size n, that is a non-increasing sequence of non-negative integers, is graphic if and only if d dash is graphic. So given a sequence d of non-negative integers arranged in non-increasing fashion, it will be graphic if and only if another sequence d dash is graphic. Now let's see what is this d dash. This d dash is obtained from d itself by deleting its largest element delta and subtracting 1 from each of its next delta largest elements. So let's see what actually is being done in this particular theorem with a very small example. Suppose d is a given sequence of n non-increasing non-negative integers. N is greater than 1 means we are dealing with sequences where at least we have 2 terms, that is we are dealing with the graphs having at least order 2. So suppose we have a non-increasing sequence of non-negative integers like 3, 3, 2, 1, 1. Now the theorem is that a given sequence d will be graphic if and only if the sequence d dash is graphic. Now how is this d dash obtained? It is obtained from d by deleting its largest element delta. Largest element means in d the largest degree value that you have. Now since it is already arranged in the non-increasing fashion, the largest element is residing in the very beginning of the sequence. So this is the largest element 3. So I am going to delete this element. So by deleting the largest element, that is 3, and subtracting 1 from each of its next delta largest element. So this delta is important. What value you are deleting? So here capital delta is 3. That is the largest element, capital delta. So you are deleting delta, that is you are deleting 3, and you have to subtract 1 from each of its next delta largest elements. That is, in this case we have to subtract 1 from each of its next 3 largest elements. So they are already arranged in non-increasing fashion. So the next 3 largest elements are these 3. So basically the value that you are deleting, that is the very first and the largest element in the sequence, that is capital delta. After you delete that, the next capital delta elements, now whatever value you are deleting, those many next elements will suffer a reduction in their values by 1 each. So I am deleting this 3, so I won't be writing this 3 again in the next sequence D dash, and these 3 elements 3, 2 and 1 will suffer a reduction in their values each by 1. So 3 becomes 2, 2 becomes 1, and this 1 becomes 0. And this reduction is suffered by only the next delta element, that is the next 3 elements, because I am deleting the value 3. And the last element present in the sequence will remain as it is without suffering any decrement. So that is how we obtain the sequence D dash, and the theorem goes like this, that if the sequence D dash is graphic, then the original sequence D is also graphic. Now how will this be helpful? This is helpful because the moment we create the sequence D dash, see the number of vertices have decreased by 1. D had 5 terms in the sequence, D dash has 4 terms. Now from D dash we can again obtain another new sequence D double dash by the same technique. Now before we apply this technique, we have to make sure that the sequence on which we are applying this technique is arranged in non-increasing fashion. If it is not, then it's your job to first arrange it. For example, here D dash is not arranged in non-increasing fashion. So I have to first arrange it as 2, 1, then 1 comes and 0 goes to the last. This is now arranged in non-increasing fashion. Now after it is arranged, I can now proceed to find the sequence D double dash, which is obtained in the similar manner as we have obtained D dash from D. So we will now obtain D double dash from D dash. So we will remove the very first element, that is the largest element. So delta is 2 in this case, and since delta is 2, I am going to subtract 1 from each of the next 2 elements. So since 2 is deleted, the next 2 elements exactly will be facing reduction in their values. So 1 becomes 0, this one also becomes 0, and this 0 does not face any reduction and remains 0. So we obtain the new sequence D double dash. See, the number of terms further reduced by 1. Now the advantage of this theorem is that the new sequence that we are creating, it is easy to check whether that sequence is a graphic sequence or not. See, a graph with 3 vertices, each of which is having degree 0, that is 3 of them are isolated vertices, definitely the graph is simple graph. And if it is simple graph, that means this sequence D double dash is a graphic sequence. The moment you conclude this is graphic sequence, then by the Havel-Hakimi theorem, this sequence D dash is also graphic sequence. Again by the Havel-Hakimi theorem, the sequence D is also a graphic sequence. So this is basically the Havel-Hakimi theorem, that given a non-increasing sequence of non-negative integers, we create a new sequence from that by following a certain technique of deletion and subtraction. And the theorem says that if this new sequence is graphic sequence, then the original sequence was also graphic sequence. So we can repeatedly apply this technique and keep creating sequences of lesser size and check whether it is a graphic sequence or not. If our current sequence is graphic, then by Havel-Hakimi theorem, all the previous sequences and hence the original sequence was also a graphic sequence. Now we will solve some problems based on the Havel-Hakimi theorem to check if any given sequence is graphic or not. So this is our first question. The sequence is 4, 2, 2, 1, 1. Our job is to check whether this sequence is graphic or not. See, there is another part of the question that if yes, if it is graphic, then we have to construct a simple graph with the same degree sequence. That is, you not only will conclude that the sequence is graphic or not, but if it turns out to be graphic, that is, if you conclude that simple graph is possible to draw with this sequence as a degree sequence, then you have to give a construction of such a simple graph which will have this as its degree sequence. Now to check for a sequence to be graphical, don't forget to first check if the sequence is degree sequence. So given such question, your first job is to name your sequence D and write it in the non-increasing fashion. Now in the question itself it is written in the non-increasing fashion, so I don't need to do any change. Now in case if it is not in the non-increasing fashion, make sure that you first name your sequence D after arranging it in non-increasing fashion. So here I have my sequence D already arranged. Then my next job is to find the sum of all the terms present in the sequence. So I have the sum here as 10, which is even. Now once it is even, you can conclude that D is a degree sequence. Now we can proceed to check if it is graphical. So in this particular very first step, if you find the sum is not even, immediately you conclude it is not degree sequence, immediately you conclude it is not graphic sequence. So no graph can be drawn also. And if it is even, then you can only proceed to check if it is graphic. So this is the foremost duty to do given such question. First, check the arrangement. If it is arranged properly in non-increasing fashion, name the sequence as D or as S, whatever you feel like. Then proceed to find the sum of all the terms. If it is even, term it as a degree sequence and then proceed to apply the Havel-Hakimi theorem to check if it is graphical. So we will now apply the Havel-Hakimi theorem. The given sequence is 4, 2, 2, 1, 1. Now how will we apply the theorem? First you will write the sequence D in the non-increasing fashion as it was. Now name the vertices, label the vertices. See, this is a degree sequence we have already concluded. So these are going to be degree values of vertices in a graph. Now if these are degree values of the vertices, definitely there will be some vertices which are having these degree values. So just give the names of the vertices which will have the corresponding degree values. Name them as V1, V2, V3, V4 and V5. As many terms you have in the sequence, those many vertices you will have in the graph. Name them accordingly from V1 to as many you have. Now why is this important? Now this labeling is not important to identify whether it is graphic sequence or not, but this labeling will be very helpful when you will try to construct the graph finally. So it is very important that you label it from the very beginning. So this is my given sequence D. Now as per the theorem, I will proceed to find out the next sequence D dash. So D dash would be, see, it's already arranged in non-increasing fashion. So in the very beginning I have my largest element, that is my delta. So here the delta is 4. So I am going to delete 4, that is 4 will not be present in the next sequence. And since I am deleting the value 4, so the next 4 elements will be suffering a reduction in their values by 1 each. So the next 4 elements are basically all the remaining elements. So 4 is deleted, next 4 elements are facing reduction. So 2 will be reduced by 1, it will be 1. Everyone is going to face a reduction by the value 1. So 2 will become 1, 1 will become 0, this one will become 0. Okay. Immediately after you create your sequence D dash, put the names of the vertices. So this was your V2, this was your V3, this was V4 and this was V5 because V1 was deleted. Okay. Next job is to check if the sequence that you have obtained, that is D dash, if it is arranged properly in non-increasing fashion or not. So here we can see D dash is already arranged in non-increasing fashion. Now if it is not, then your job would be to arrange it. Okay. Now here it is already arranged. So I can proceed further. So I can find out D double dash. So D double dash can be found out by removing B2, that is the largest element in this sequence now. And since I am deleting 1, the value 1, so the next 1 element will face reduction. So the single element is going to face the reduction. So 1 will be reduced to 0 and these zeros will remain as it is. They are not facing any reduction because I have deleted the value 1. So next 1 element faces the reduction. Remaining will remain as it is. The moment you create your new sequence, name the vertices. These are V3, V4 and V5. Okay. Now I have obtained the sequence D double dash where I see all the terms are 0. So I can stop here now. Now it's up to you, where do you want to stop? You could have stopped after finding out D dash only. The idea is you can stop at whichever sequence when you find that you are confident enough to say whether that sequence is graphic or not. So looking into D dash itself, if you can say confidently that this is a graphic sequence, you can stop there only. You should not have then found out D double dash. But if you are not confident, proceed further, find the next sequences D double dash, D triple dash, everything. Okay. So this is the very first problem we are solving. So I have reduced it till D double dash when all of them are 0. Now once you get all of them is 0, there is no advantage of proceeding any further. So now see the sequence D double dash isn't it easy for me to check whether this sequence is a graphic sequence? See, there are 3 vertices, each having degree 0, that is 3 isolated vertices. Is not the graph simple? Yes, the graph is definitely simple. So if a simple graph can be drawn with this sequence d double dash, then definitely a simple graph can be drawn with the sequence d dash also, then definitely a simple graph can be drawn with the sequence d also. That is Havel-Hakimi theorem. So if d double dash is graphical, that means d dash is graphical, that means d is graphical. So our original sequence is graphical because this sequence d double dash is graphical. So that is solution of one part of the question. So you can write the reason that d double dash is graphical because a simple graph can be drawn with this degree sequence, which implies d dash is graphical, which implies d is graphical. Now these two conclusions are following from Havel-Hakimi theorem itself. Okay. Now the second part of the question, that is draw the graph. If you are saying that a simple graph is possible, construct such a graph for the sequence d. So how can we construct the graph, the simple graph with this degree sequence d? So we will first start drawing the graph for the degree sequence d double dash. Now see, in d double dash there are 3 vertices, 1, 2, 3. The names are V3, V4 and V5. The values indicate that their degrees are 0 each. So these 3 vertices are isolated vertices. So what I have drawn now, this is a graph which is simple graph corresponding to the degree sequence d double dash. This graph satisfies the degree sequence d double dash. Now I will modify this graph itself to create the graph for d dash. How? See, d dash was having an extra vertex, that is V2. V2 was deleted, then we have obtained d double dash. So if we want to draw the graph for d dash, then we have to enter the vertex V2 that was deleted. Now the moment you enter the vertex V2, see, the adjacency of V2 would be with those vertices who have suffered reduction because of its deletion. That means when V2 was deleted, some vertices have faced reduction. See, after deletion of V2, V3 faced a reduction in its value. So when V2 will enter, V2 will be adjacent to that vertex only, or to those vertices only which have faced reduction in their values because of its removal. So V2 enters and V2 becomes adjacent to V3. See, this is the graph which satisfies the degree sequence d dash. V2 is having degree 1, V3 is having degree 1, V4 and V5 they are having degree 0s. So 1, 1, 0, 0, this degree sequence is satisfied by this graph. Now we will again modify this graph to create a simple graph for the sequence d. Now the sequence d had another vertex V1 which was deleted, and we have created the sequence d dash. So to have the graph for d, we will have to insert that vertex V1 back which was deleted. Now when V1 was deleted, the 4 vertices V2, V3, V4 and V5 have suffered decrement in their values. So when V1 enters, it enters with a degree 4 and it becomes adjacent to all those 4 vertices who have suffered reduction in their values because of the deletion of V1. So V1 enters and becomes adjacent to all those 4 vertices V2, V3, V4 and V5 who face the reduction. So V1 becomes adjacent to V2, it becomes adjacent to V3 and to V4 and also to V5. See, this is the graph that we obtain for the sequence d. Let's check if it satisfies the degree sequence d or not. So V1 is having degree 4, V2 is having degree 2, V3 is having degree 2, V4 is having degree 1 and V5 is also having degree 1. So we see the degree sequence is 4, 2, 2, 1, 1. See, same as d, 4, 2, 2, 1, 1. So this is a simple graph that we have drawn without loops and multiple edges, that is having d as its degree sequence. So this is the solution to the next part of the problem, that we have constructed a simple graph having the degree sequence as given in the question, that is d. Let's solve some more problems to even understand this process better. So this is another question where we are given a sequence to check if it is graphical. If yes, we have to construct the simple graph. So our very first job is to find out the total sum of all the elements present in the sequence. Now here the sum is 24, which is even. So the given sequence is a degree sequence. That is our conclusion. So if we name the sequence as d, then d is a degree sequence. So now we can proceed to check if it is a graphic sequence or not. So check if your sequence is already arranged in non-increasing fashion. So here I can see it is already arranged. So I have written here the sequence D in the non-increasing fashion as provided in the question itself. So I need not do any rearrangement, and I have placed all the labelings of the vertices. There are 10 vertices, so I have named them from V1 to V10. Now we proceed to find out the next sequence, that is D dash. So D dash would be obtained by deleting the very first, that is the largest element 5. Since you are deleting 5, the next 5 elements will face reduction in their value. So these are the next 5 elements. So it's better if you give a cross for the element that you are deleting and you give a bracket or just denote the elements which are going to face a reduction. So that would be easy for you to understand and to compute the next sequence. So 5 is deleted, that is the vertex V1 is deleted. Next 5 are going to suffer a reduction. So this becomes 3, 2, 2, 1, and the rest will remain as it is. After creating the sequence, label the vertices. So you have V2, V3, V4, V5, V6, V7, V8, V9 and V10. See if it is arranged properly. No, it is not arranged in the non-increasing fashion. So my next job would be to rewrite D dash in the rearranged manner. So I have 3, then 2, 2, then the 2 comes first, 1 goes later, and the remaining ones are here. So this 2 has come here. Okay, now labeling. This is V2, V3, V4. Now see, when you have shifted 2 from the later position to a much former position, not only the value 2 comes, but it takes with itself the labeling also, right? So when 2 comes here, the labeling V7 also comes in that position, and when this 1 goes here, V5 goes there. So this is V5, V6, then V8, V9, V10. This is very important to keep in mind. That is, whenever you are rearranging a sequence, first thing to keep in mind is to rearrange. That is something that you should not forget. Now another thing, when you rearrange, make sure the labeling also moves along with the degree value. So this is the rearranged sequence. Let's now find out the next, that is D double dash. Delete the very first, that is the largest. You are deleting 3 here. So next 3 elements will face reduction. So they will turn 1, 1, 1, and the remaining all are 1s. So I will keep them as it is. Next job, label V3, V4, V7, V5, V6, V8, V9 and V10. Now see, all of them are 1. If you wish, you can proceed again further to find D triple dash. It is already arranged in non-increasing fashion. Else you can stop here if you are confident enough that yes, you can check whether this is a graphic sequence or not. So what I am doing is I am stopping here. I can check from here whether this is graphic or not. Let's see by drawing the graph, it would be more clear. If you wish, you can proceed 1 or 2 steps more and see how the sequence will get reduced, and you will be left with some smaller sequence. So let's now check if I can draw a simple graph with this sequence D double dash as the degree sequence. Now if I can draw a simple graph, then D double dash will be graphic sequence, and then by Havel-Hakimi theorem, D dash will also be graphic, and the original sequence D will also be called graphic. So here I have the sequences D, D dash and D double dash already written. So let me just draw the graph. We are having 8 vertices in total. So let me draw 8 vertices. It's always beneficial to put the vertices of a graph in a circular fashion. Now see, all of these vertices are having degree 1 each. How can I create such a graph so that all of these vertices will have degree 1? See, there are even number of vertices. If I pairwise make them adjacent, I can have every vertex having degree 1. See, here are 8 vertices, each having degree 1. So this graph which I have drawn satisfies the degree sequence D double dash. So we can see a simple graph is possible with D double dash as the degree sequence. That means D double dash is graphical, which means D dash, and hence D is also a graphic sequence by Havel-Hakimi theorem. So first part of the question is solved, that D is graphic. Now how to draw the graph? So we have already drawn the graph for D double dash. Now modify it to create the graph for D dash. Now when you create the graph for D dash, check that step where you have deleted a vertex. Now we have deleted the vertex V2, and because of its deletion, next 3 elements suffered reduction. So I will insert the vertex V2. Okay, I have not named the vertices, so it's better if you name all of them: V3, V4, V7, V5, V6, V8, V9 and V10. These were the vertices as per the sequence D double dash. Now to create this graph for D dash, V2 has to enter. So I am making the entry of the vertex V2. Now V2 will enter with a degree value 3, as we can see here, that was deleted. And because of its deletion, V3, V4 and V7 phase reduction. So when V2 will enter, this V2 will have degree 3, that is made by making V2 adjacent to those 3 vertices which phase reduction. So V2 will enter and will be adjacent to V3 and to V4 and it will be adjacent to V7. So this is the graph corresponding to the degree sequence D dash. Okay. Next we have to create the graph for D. So to create the graph for D, we need another vertex V1 that was deleted. So let us make the entry of V1. V1 has degree 5 and it will be adjacent to all those 5 vertices which phase reduction. See, now the labeling is helping us to draw the adjacencies. We know V1 will enter and V1 will be adjacent to V2, V3, V4, V5, V6. So I enter V1 and I make it adjacent to V2, V3, V4, V5 and V6. See, this is the graph that we obtain for the degree sequence D. We can cross check by calculating the degree values. V1 is having degree 5, V2 is having degree 4, calculate very carefully. V3 has degree 3, V4 has degree 3, V5 is here having degree 2, V6 is having degree 2, V7 has degree 2, V8 has degree 1, V9 and V10 also have degree 1. Now if we write the degree sequence of this graph, we have 5, then 4, 3, 3, 2, 2, 2, 1, 1, 1. See, it completely matches with the given degree sequence D. So this is the simple graph that we can construct having degree sequence equal to the given sequence in the question D. So this is the second part of this solution. Let's see another problem. So here we have the total sum as 20, which is even, which indicates this sequence D is a degree sequence. So we move to check if it is graphical. We have written the sequence here. We have checked already that it is in the non-increasing fashion. So we proceed to find out the next sequence, that is D dash. So we delete the very first largest, it is 3. So the next 3 will phase reduction. They will turn 2 each. Then the remaining will remain as it is. The moment you create the sequence, name the vertices. Next job is to check if it is arranged. As I can see, it's not arranged. So I will arrange it in the non-increasing fashion. First 3 comes, then 2, 2, 2, then the 2, 2 and then 1. Label them correctly. So 3 comes with the labeling V5, then this 2 corresponds to V2, then V3, V4, then this is V6, V7 and then we have V8. Now it is arranged in non-increasing fashion. So proceed to find out D double dash. So we delete the first element, that is the largest 3, and we subtract 1 from each of the next 3. So we have 1, 1, 1, then 2, 2 and 1. Labelings are V2, V3, V4, V6, V7 and V8. It is not arranged, so you can arrange it. So you will be having first 2, then 2, 1, 1, 1, 1. Labelings will be V6, V7, then comes V2, V3, V4, then V8. Now if you wish, you can proceed further to calculate D triple dash. I will stop here and I will try to draw the graph and check if it is graphic. So here are the sequences that we have. As I can see, D double dash is having 6 vertices in total. So I draw 6 vertices, name them V6, V7, V2, V3, V4 and V8. Okay. Now out of these, V6 and V7, they have degree 2 each. So I can make the degree value of V6 2 by making it adjacent to suppose V7 and maybe V8. Okay. V7 also has degree 2, so make it adjacent again to V2. See, V6 and V7 are having degree 2 each, and rest all will have degree 1. See, V8 and V2 are already having degree 1. How can I make the, this was V4. How can I make the degree value of V4 and V3 also 1? By making them adjacent to each other. See, here now we have 2 vertices of degree 2 each, that is V6, V7, and the rest of the 4 vertices are having degree 1 each. Now this is the graph which is simple and we can draw it with the degree sequence d double dash. So d double dash is a graphic sequence, hence d dash, and hence d is also a graphic sequence by Havel-Hakimi theorem. This is the first part of the solution. Next, we modify this graph only to create our graph for d. Before that, we need the graph for d dash. So V5 will enter, which was deleted, and V5 has degree 3. So it is adjacent to those 3 vertices which face reduction. So V2, V3 and V4. So V5 will be adjacent to V2, search for V2 and make it adjacent to V2. It will be adjacent to V3 and it will be adjacent to V4. So this is the graph corresponding to d dash. And then we will construct for d. So we will insert the vertex V1. It is going to be adjacent to V2, V3 and V4. So make it adjacent to V2, V3 and V4. Okay. Now cross check by writing the degree values. V1 has degree 3, V2 has degree 3, V3 has degree 3, V4 has degree 3, V5 has degree 3, V6 has degree 2, V7 has degree 2 and V8 has degree 1. So the degree sequence is 3, 1, 2, 3, 4, 5 times. So we have 5 times 3, then we have 2 times 2 and we have 1 time 1. So this is same as the degree sequence given by our d. So this is a simple graph that is constructed with d. That is the second part of the solution. Let's see another problem. Here the sum total is 30, which is even. So our given sequence d, suppose, is a degree sequence. Now proceed to check if it is graphic. So we have seen it is already arranged in the non-increasing fashion. So we label the vertices accordingly and we proceed to find out d dash. So we delete the first. Next 7. So there are 1, 2, 3, 4, 5, 6, 7 elements in total remaining. So all of them will face reduction. So this will be 6, then 3, 2, 2, 2, 1, 0. Okay. Immediately write the names of the vertices V2, V3, V4, V5, V6, V7 and V8. See if it is arranged. Yes, it is. So we proceed to find out the next sequence d double dash. Delete 6. Next 6 elements will face reduction in their values. So this will be 2, this will be 1, 1, 1, 0, and this 0 is also to face reduction, and the result to it is -1. Now as per the technique, since 6 is deleted, next 6 elements have to face reduction. If there is 0, you have to reduce the value and you will be getting -1. The moment you get negative value in your sequence, definitely it is not a degree sequence of any graph, because degree value of any vertex can never be negative, and whatever figures we are dealing with, they are all degrees, right? They are degree values of certain vertex. So if it comes negative, that means this sequence is not a degree sequence. So we conclude here that d double dash is not a degree sequence, because a graph having a negative degree value is not possible. So if it is not a degree sequence, it implies d double dash is not a graphic sequence. A sequence which is not a degree sequence can never qualify for being a graphic sequence. Now if it is not graphic, it implies d dash is not a graphic sequence, which implies d is also not a graphic sequence. That is Havel-Hakimi theorem. So a sequence d will be graphic if and only if the sequence d dash that is created next is graphic. So if it is not graphic, d will also not be graphic. So our solution to this is the given sequence, although is a degree sequence, that is graph is possible with the sequence d, but simple graph is not possible. So it is degree sequence only, but not a graphic sequence. And since it is not a graphic sequence, construction of such simple graph doesn't even come into the question. So that is the complete solution to this problem. We have to conclude that the given sequence d is not a graphic sequence. Let's see the next example. So here we are given the sequence d, where the sum total is 24, it is even. So no doubt the given sequence is a degree sequence. Proceed to check if it is graphical. We see it is already arranged in the non-increasing fashion. So we proceed to find out d dash. Delete the first element 5. Next 5 will suffer reduction. So it will be 4, 3, 2, 1, 1, and these two will remain as it is. Immediately name them V2, V3, V4, V5, V6, V7 and V8. Next, see if it is arranged. It is not. So I have to arrange the sequence. First 4 comes, then 3, 2, then this 2 comes earlier, 1 goes later, and then another one, and we have the remaining 1. Again, name the vertices correctly, V2, V3, V4, up to this it is fine. This 2 has been shifted with the labeling V7, this 1 has been shifted with its labeling V5, then V6 comes, and finally V8. Next, now since it is arranged in non-increasing fashion, I will proceed further to find out the next sequence D double dash. So 4 is removed, that is the vertex V2 is removed. Next 4 vertices face reduction, so we have 2, 1, 1, 0, 1, 1. The last 2 remain as it is. Name the vertices V3, V4, V7, V5, V6, V8. It is not arranged properly, so I will arrange it. 2, then 1, 1, then these 2 ones come, 0 goes to the last. So this is V3, V4, V7, these are V6 and V8, V5 goes at the last. If you wish, you can proceed further to find the next sequence, that is D triple dash. Well, I will stop here and I will try to draw the graph. So these are the sequences. Now if I see D double dash, here I have 6 vertices in total. Names of the vertices are V3, V4, V7, V6, V8 and V5. Here I can see V5 is having degree 0. So V5 will be an isolated vertex. Next, V3 is having degree 2, so V3 has to be adjacent to 2 vertices of the graph. You can make it adjacent to any 2 vertices you want. Okay, that makes the degree of V3 2. V4 is having degree 1 already, V8 is having degree 1 already, and V6 and V7 are to have degree 1 each. So I make them adjacent to themselves and I make their degree values 1 each. So this is the graph corresponding to the degree sequence D double dash, which I can clearly see is a simple graph. So D double dash is graphic sequence, which means D dash is graphic, and which means D is graphic by Havel-Hakimi theorem. That is the first part of the solution. Now we draw the graph. So we modify this to create the graph for D dash. So the vertex V2 enters with degree 4 and it becomes adjacent to V3, V4, V7, V5, which face reduction. So V2 becomes adjacent to V3, it becomes adjacent to V4, it becomes adjacent to V7, and it becomes adjacent to V5. So this is the graph corresponding to the degree sequence D dash. Now to create the graph for D, insert the vertex V1 that was deleted. It will be of degree 5 and it will be adjacent to these 5 vertices, that is V2, V3, V4, V5 and V6. So make V1 adjacent to V2, V3, V4, V5 and V6. Now after you have drawn, don't forget to cross check by writing the degree values. V1 has degree 5, V2 has degree 5, V3 has degree 4, V4 has degree 3, V5 has degree 2, V6 has degree 2, V7 has degree 2 also, and V8 has degree 1. So the degree sequence is 5, 5, then 4, then 3, then comes 2, 2, 2 and finally 1. Check if this matches with the given degree sequence D. So it completely matches with D. This is our sequence D itself. So this is the simple graph that is constructed with the degree sequence D. That is the second part of the solution. Let's see another sequence. So here the sum total is 24, which is even. So the sequence D here is degree sequence. Let's see if it is graphic sequence. So it is already arranged in non-increasing fashion. We proceed to find D dash. So we delete 5. Next 5 will be reduced by 1 each. So we have 4, 3, 3, 1, 1. And the remaining 2 ones remain as it is. Name the vertices V2, V3, V4, V5, V6, V7, V8. Next we see it is already arranged in non-increasing fashion, so we don't need any rearrangement. So we proceed to find D double dash. We delete 4. Next 4 will face reduction, so we will have 2, 2, 0, 0, 1, 1. Name them V3, V4, V5, V6, V7, V8. Now we see it is not arranged, so we will arrange the same sequence in non-increasing fashion. So we get 2, 2, then 1, 1, 0, 0. Here the labelings have to be done carefully. V3, V4, then comes V7, then V8, and then we have V5 and V6. So again, if you wish, you can proceed much further to find out D triple dash. Well, I will stop here and I will start drawing the graph. So these are the sequences I have. As I can see, D double dash is having 6 vertices in total. So let's draw those 6 vertices. Names are V3, V4, V7, V8, V5 and V6. Here we see V5 and V6 are isolated vertices having degree 0. Then V7 and V8 are having degree 1 each, and V3 and V4 are having degree 2 each. How can we make the degree of V3 2? By making it adjacent to V4. And since I can't make them adjacent to V5, V6 because they are isolated vertices, so let me make V3 adjacent to V8. Okay, so V3 has degree 2. Now V4 has degree 2, so V4 is already adjacent to V3. Let me make it adjacent to V7. I cannot make V4 adjacent to V8, otherwise V8 will have degree 2. Okay, so make V4 adjacent to V7. Now in that situation, V3 and V4 are having degree 2 each, V7 and V8 are having degree 1 each, and V5 and V6 are isolated vertices with degree 0 each. So this is a simple graph satisfying the degree sequence D double dash. So D double dash is graphical, hence D dash is graphical, hence we can conclude the given sequence D is a graphic sequence, or it is graphical. Next, to draw the graph, this is the graph for D double dash. So to draw the graph for D dash, we insert the vertex V2 that comes into picture with a degree 4. It becomes adjacent to those vertices which have phase reduction due to its deletion. So it becomes adjacent to V3, V4, V5 and to V6. This is the graph for the sequence D dash. Then for D, I need the entry of the vertex V1, which will be of degree 5, and it will be adjacent to V2, V3, V4, V5 and V6. So make V1 adjacent to V2, V3, V4, V5 and V6. Now let's cross check by calculating the degree values. V1 has degree 5, V2 has degree 5, V3 has degree 4, V4 has degree 4, V5 has degree 2, V6 has degree 2, V7 and V8 are having degree 1 each. So the degree sequence of this graph becomes 5, 5, then 4, 4, then 2, 2 and then 1 and 1. So it matches completely with the degree sequence D. So this is the simple graph for the given sequence D. So I hope that Havel-Hakimi theorem is quite clear to you. Keep practicing such problems because this is quite a vital theorem of graph theory, checking whether a sequence is graphic or not. That is, it's not enough to just check if a sequence is degree sequence. It's important to check if you can draw a simple graph or not. Now that is the trick. Drawing a graph is easy using loops and multiple edges. Trick is whether a simple graph can be drawn or not. So in that case, Havel-Hakimi theorem is of vital importance. So do practice such problems more and more, and I hope it will be very clear to you. It's quite an interesting theorem, and the way of solving these problems is also quite interesting and easy. So try to solve it and try to maintain the pattern which I have used to solve these problems. For example, like labeling the vertices, it will be very important and it will be very beneficial to you when you will try to construct the graph. Okay, so try to label the vertices and keep the labeling perfect when you swap the degree values, that is when you rearrange some sequence. So don't forget to rearrange them with their labelings. So this is what Havel-Hakimi theorem is all about. Now for your practice, I will be posting some problems. So now we have arrived at the problem for practice session. I am posting here 2 problems based on Havel-Hakimi theorem. There are 2 sequences given here. You have to check if these sequences are graphic sequences. So first check whether they are degree sequences by finding out the sum. Then check whether they are graphic or not by the application of Havel-Hakimi theorem. Now if they turn out to be graphic, then you construct the simple graphs that will have these sequences as the degree sequences. So solve this problem separately, and I will discuss with you the solution to this problem in the very next lecture. So that's all for today. I really hope that you are enjoying these lectures. Do keep practicing problems more and more on these graphic sequences, degree sum formula and everything. So these topics will be more clear if you practice more problems. So I am going to meet you again with some new topic in the next lecture of this series. Till then, if you have any queries or suggestions, please do let us know by writing in the comment section below. And if you love learning with me, then please do like, share and subscribe to our channel. So I am going to meet you again soon. Till then, thanks for watching. Take care and bye-bye.